All right, if I haven't already hurt your mind yet, let's cause some more havoc in your brain. So here's a new one. Boiling and evaporation. We're going to use those hand in hand. Technically, there's a difference between them, but for HVAC and right now, simplicity, we're going to put them together as with one word. Boiling and evaporation. Every time a substance changes state from a liquid to a vapor, it absorbs heat. We talked about it already. That's called the latent heat of evaporation. It's hidden heat, latent heat. The heat's going somewhere. It's going into the change of state. But that is a cooling effect. Boiling and evaporation is a cooling effect. Yes, 100% it is. It is a cooling effect. Now this blows people's mind. Like, no, it's not. It's hot. You have to separate your feelings from science and HVAC. Okay, so when we had that water boiling, and if I was to put my hand in it, it would hurt. It would burn. Heat from the 212 degree water would go into my 98 degree hand, and it would severely cause massive pain, burning, and probably long-term damage. Don't do that, okay? But you have to think of according to the water and its own point. Its saturation temperature is 212. The point that it changes state from a liquid to a vapor is 212. No matter how much heat we put into that, it was boiling. It was changing state from a liquid to vapor. As that turned to a vapor, it was pulling heat away. It kept it at a cool 212. We couldn't raise the temperature of that above 212 until all of the water was gone. All right, so let's think about this another way. Now, surely you know, you've been at some point in time, you've had to cook some top ramen, right? You've put it in the pan. For-profit HVAC schools, they make sure that instructors are paid so low they only get top ramen anyway. So very familiar with this product right here. So let's think about, we have two pans, right? And in both the pans, we have this pan that's bigger. My wife specifically said I was not allowed to put a torch on her pan, so we can't make this exciting like the last one. But if we filled this pan full of water and we put our ramen in it, and we had this pan with some water and we put our ramen in it, we turned our stove on and we followed the directions to the temperature, let it start boiling, and then we walked away. Now we're doing something else, we get distracted, we forgot about it. Please tell me I'm not the only one that's happened to. So now what's happened to these two is the water's changing state from liquid to vapor. It's staying at 212. They know that it's at 212 degrees exactly how long at 212 it needs to cook this material. So what's happening though is it's cooking away, everything's good, but here's the deal. We're losing water. It's changing state from a liquid to a vapor. The water level is physically dropping. Now this is a larger pot. It's going to take a lot longer for that water to completely disappear. This pot over here is a whole lot smaller. Eventually, if I leave this on for long enough, the water is going to change state from a liquid to vapor, and eventually all the water will be gone. Once all of the water is gone out of this pan, will it be at a nice cool 212, or will it rise higher? If you said rise higher, you're correct. Now that there's not water to keep it at a nice cool 212, the temperature of this pan is going to increase, and then the temperature of the noodles is going to increase above 212 degrees Fahrenheit. And what's going to happen is the temperature is going to continue to go up and continue to go up and continue to go up until the ramen is actually going to catch on fire. And then you have to move and find a whole other house, which hopefully you don't have to go that far. Don't cook and forget about it. Actually, in New Zealand, they have warnings. If you come home drunk, don't start cooking because you might fall asleep and burn your house down. It's a real problem, people. Just saying. Okay, so this one's going to take much longer, but eventually the same thing could happen. All the water is going to boil away, the temperature is going to go up higher, and it's going to start to burn. So that water, having that water in there, having that water changing state from a liquid to a vapor is a cooling effect. That's what's keeping it a nice cool 212 degrees Fahrenheit. So we got to think about water as a cooling effect. Now, we have refrigerant, which is liquid refrigerant going to be flowing through this evaporator coil. And what's happening is this liquid refrigerant is going to be boiling, except that's a very low boiling point. Let's just throw a number out. Let's say it's boiling at 40 degrees, and we're putting 70-degree air across it. That refrigerant inside is going to be boiling, which means the refrigerant is going to be changing state from a liquid to a vapor, which means it's absorbing heat. It's absorbing heat away from the air. So the air temperature comes out cooler. Where did the heat go? It went into the refrigerant. The refrigerant changing state. We talked about this suction line being a vapor line or a gas line, because now that it's in a full vapor state, all the heat is in that refrigerant as a vapor state, but it's still low pressure, low temperature. But the refrigerant's boiling. You can literally touch it and feel it boiling, and it's going to be cooler than your hand. It's boiling, but heat is leaving your hand and going to the cooler refrigerant. So we can't think, water doesn't just boil at 212. But anytime we have water boiling, it is a cooling effect according to the water. Keep yourself separate from it, and it makes a little bit more sense. Now, it's not just boiling. They don't call this a boiler because the word boiler is already used. The plumbers got there first. They took the word. So we call it evaporator because the refrigerator is still changing state from a liquid to vapor. It's evaporating. It's changing state. So we call this evaporator. You're going to still hear some old school guys talk about this. Hey, what's your boiling temperature? Let's talk about what temperature refrigerant's boiling at. What's your evaporator temperature? What temperature the evaporator, refrigerant, and evaporator is boiling at? These are words that are all interchangeable. The quicker you come to accept this, the easier HVAC is going to be for you. Now let's continue with this concept of boiling and evaporation is a cooling effect. This is very, very important. Let's say that we're in the shower and we have water temperature. And for that water to be warm, it's going to be warmer than our body temperature. Our body temperature is 98.7. The water temperature is going to be higher than that. I don't know exactly what it's going to be, but let's just call it a number. Let's say it's 102. The 102 degree water temperature, it's warm, it feels great. Now when you shut the water off, you don't have any clothes on, I'm not going to demonstrate that part, sorry. You shut the water off and now you come out of the bathroom and you notice a difference. You start to cool off. And then as you continue to leave the bathroom and go into, say, the hallway, you're going to notice a big difference. You're going to feel a whole lot cooler. What's happening is all that moisture that's on your skin, all that water is going to start evaporating, changing state from a liquid form to a vapor form. As you change the state from a liquid to a vapor, it's absorbing heat. 970 BTUs for every pound of water that changes state or evaporates. So it's very significant. Now if you put a fan on top of that, you're going to have much more air moving across it, which is going to speed up evaporation. Your body temperature literally drops. It's physically pulling heat away from your body. Now if you stay in the shower, there's a lot of steam here. If you close the curtain or the door, you maintain that steam. There's a whole lot of moisture in the air. The evaporation process will slow down. But if you go outside and even into a fan where it's drier humidity, that evaporation speeds up significantly, and you can feel that evaporation is a cooling effect. That water, let's say you're sitting in your back porch and it's hot and it's a dry climate. Take a spray bottle, set it for a mist, and if you spray it in a mist, these very fine droplets very easily evaporate. What's happening is those fine droplets of water evaporate, and for every 1 pound of water that evaporates from a liquid form to a vapor form absorbs heat. 970 for every pound of water evaporation. So you can actually cool yourself off with evaporation of water. If you go to some restaurants, you'll notice you go there and they'll have outside, especially in Phoenix, you'll have these misters spraying and they'll be spraying a mist of moisture out. Well, the idea is not that the water is keeping you cool, but as that water evaporates, changes state from a liquid to a vapor, the water absorbs heat. That is latent heat, and that is also a cooling effect. We also have evaporative cooling systems that just work off of water. Places that are dry like Phoenix and Las Vegas, these work pretty well. The fact that you have water sitting in and you run water over a pad, as you pull air across that water in that pad, the water evaporates, changes state from a liquid to a vapor. It absorbs heat. It absorbs heat away from the air. The temperature of the air literally drops. So the cooler air now then distributes throughout the house. The bad part of that is the humidity in the house goes up. The heat's still there. It's just hidden in the change of state. The humidity goes up. These don't work very good in places like Florida because the air is already full of moisture. You have an evaporative cooler trying to put more moisture in the air only makes the air more humid, and there's very little evaporation, so there's very little heat transfer there. It doesn't transfer from sensible to latent anymore. Lots of more that we'll go into about evaporation. Let's move on to the next subject.